David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to catch up with notes or write down some questions. Third, you can turn on the captions and read my words on the screen. Today's lesson covers using the Sine Rule to solve more complicated situational type word problems. So let's take a look at our first one. I've got this diagram. Here's a shoreline. So all this is the land. All of this is the ocean. And I've got a boat out here at point C. And then I have some numbers here. I have point A, a straight line to the boat from point A makes a 65-degree angle with the shore. And the same thing from point B to the boat, it makes a 42-degree angle with the shore. And then we've also been able to measure this distance along the shore. So this is actually a real type scenario. If you wanted to find out a few things, you could make these measurements from the shore with the boat out there without ever going to the boat. Okay, so now let's take a look at the problem we're being asked to solve. And here it is up here. If Judy can swim at 1.25 meters per second, how long will it take her to swim from the boat to the shoreline? So that's the problem we're being asked to solve. And if you're feeling super bold and you know how to use your Sine Rule, go ahead and pause the video right now and see if you can solve this entire problem. I'm going to walk you through all the steps, but if you feel like you could do it, I would say give it a shot and then come back and start the video up again and see how you did. Okay, so let's analyze this a little bit. Check her out. The swimmer, Judy, she needs to swim from here to there. That's her quickest approach. So that line isn't even on the diagram. You need to figure that out. And that's going to be a straight line to the shore, which is going to make a 90-degree angle with the shore. So that gives us a triangle within our triangle that we're going to have to find one of the side lengths of, that one. Now, I can't really do that directly yet because I just don't have enough information. In fact, I don't know where this line crosses this 200-meter line. I have no idea about that angle or that angle, so I really don't have anything I can use. But what would be nice is if I knew this side or this side, then I could start thinking about this little triangle that's inside our bigger triangle. And that's where the Sine Rule is going to come into play. Remember our Sine Rule. It's just the length of one side is over the sine of the opposite angle equals the length of another side over the sine of the opposite angle, and so on. So I'm thinking maybe I'm going to need to use the Sine Rule to jump into this triangle and perhaps figure out this side or that side, and then I'm in business. Once I know one of these two sides, then I can start thinking about this little smaller triangle inside so I can figure out what that length is. Once I know that length, then I can use the fact that she swims at 1.25 meters per second to find out how long does it take her to swim from here to here. Okay, so let's take a look. Sine Rule might be, I'm just going to pick this side. This is the one that I want to find. Okay, so I put an X there. So I'm going to do X over sine 65 is going to equal, that's the side I want, is going to be 200 over sine O. I don't know angle C. Pause the video. Angle C is easily achieved from this diagram. See if you can figure that out. Let's see how you did. What you needed to remember was that all 3 angles inside any triangle on the planet add up to 180. So if we just take 180 and we subtract the 2 that we know, we get the one that we don't know, which is 73. So this is going to be sine 73 right there. So now, if you're riding along and you haven't already done the problem, pause the video and solve this one for X. So I get X is 189.5 meters. Now notice how I am carrying 4 significant digits from this calculation. And I'm doing that on purpose. I'm going to round to 3 sig figs when I get to the end. If I carry 4 all along the way, I'm going to have an answer that's much more accurate. Okay, so now that we know that X is 189.5, we can start to figure out what this distance is here. And I'm just going to call that one y. Why not? There's my y. So pause the video and write an equation that helps you find y, and maybe even solve that equation and tell me what y is. All right, to find y, you just use regular old SOHCAHTOA trigonometry. I have a right triangle right in here, so I know that sine of 42 is opposite over hypotenuse, so my y is the opposite, the one I'm after, and the hypotenuse is the one that I found in this step here. So I would just write sine 42 equals y over 189.5, rearrange this equation to solve for y, pull out my calculator. Now y is 126.8 meters. There we go. There you have it. Oh, you realized I'm not done. I'm glad you did. Take a look at the problem and tell me what the answer would be. All right, let's go back to a very basic distance, rate, and time equation. The time for a trip is the distance divided by the rate. So our time is going to be our distance, 126.8 meters divided by 1.25 meters per second. That gives me 103 seconds, which is 1 minute, 43 seconds. So that's how long it takes Judy to swim from the sailboat to swim 126.8 meters to the shore. All right, let's attack another problem. This one is also a very real problem. In fact, you're going to learn one of the techniques that we use to measure the distances to far away stars. Okay, so it's pretty cool. So let's take a look at this diagram. This has all the realistic bits in it. Here's a star that's super far away, and then here's our sun right there, and here's our Earth, which rotates around the sun like that. Okay, now we have some distances to talk about here. The distance from the Earth to the sun is 1 AU. That's an astronomical unit. It's about 93 million miles, and that's the distance from the Earth to the sun. So the distance from the Earth's one side of its orbit around the sun, say like at the winter solstice, all the way across to the other one, say at the summer solstice, that's 2 AUs, that distance. So you can see here that this makes a big triangle here, with the base of this triangle being the diameter of the Earth's orbit around the sun. So pretty cool. Large scale, right? I mean, we can't walk 93 million miles. We can't go there, but guess what? We're riding on this planet that's cruising around the sun pretty darn quick. So we do travel 93 million miles all the way around. Actually, we travel twice that across the disk of our solar system. So check this out. Here's the thing, is that with fancy telescopes, astronomers can look at this star when they're at this solstice, and they can look at the background stars because they're stars that are behind it from this angle. And then they make another observation from 6 months later, and they look at the same star and they see how the background stars have changed. And that shift allows them to measure this angle. It's called the parallax angle, and they can get this angle P. So they can use that and some trigonometry to figure out how far we are, this distance, to the star itself. So first step, what I would like you to do is take this diagram and reduce it down to a triangle with its basic elements that you would need to start thinking about some trigonometry. I'm not telling you any numbers yet, but I'm asking you to reduce this down to a place where you would be able to see all the essential components to then start working your trigonometry on it. All right, so here is that triangle. This is distilled directly from this, but I took away all the extra details that kind of set up the context of this problem. So check it out. I have this base here is 2 astronomical units across, all the way across like that, 2 of them. And then here's a distance. Let's go ahead and label the distance that we're after. That's the x. This is where we are at this point, and we want to know the distance to that star. Okay? And that would be the same as this distance to the star. Okay? So on our triangle here, I've got 2 x's. That is our distance. And then I labeled our little P angle right in there, our parallax angle. That's right there, okay? So that's pretty much all you need there, okay? So now I'm going to give you some information and ask you to perform the calculation. Okay, here are the two things you need to know. One astronomical unit, I converted this to metric, is 1.5 times 10 to the 8 kilometers. That's about 150 million kilometers for 1 AU. Now this angle P, measured by our telescopes by flitting back and forth across the disk of our solar system, is about 1.2 times 10 to the minus 4 degrees. Very tiny little angle, but they have really cool stuff, cool instruments that can actually measure angles that are that small. Pretty neat. Okay, so now you have everything you need to find this distance. So go ahead and give that a shot. Okay, let's see how I took that calculation so far. I've used this information and this triangle to sort of do some thinking and some calculating and some figuring out of stuff. First off, you need to recognize that that's an isosceles triangle. I have two equal angles and I have two equal sides across from them. So I'm going to exploit that in a minute. So first off, I need this base. That's going to be helpful. That's 2 AU. So that's 3 times 10 to the 8th kilometers. That's just twice 1 AU. And now I need to find out what my base angles are. And this is going to be kind of weird because they're going to be almost 90-degree angles. Almost 90. So I'm going to, again, just like in that last problem, exploit the fact that the whole triangle has 180 degrees in it to figure out what these two angles are. Okay? So 180 minus twice this little thing, this little P angle, is going to be this angle plus that angle. So that's all I've written here is 180 minus twice the tiny angle equals angle A plus angle B. Now here's an interesting thing. Since we know that angle A and angle B are equal, on my next step, I just did twice angle A because they're equal, so I can just substitute a second angle A in for the B here and just write 2A there. Then I did my math a little bit more. This is 180 minus 0.00024 degrees. I put that into a decimal so that it's easier to see. What comes next is that this twice A is 179.99976 degrees. That's twice A. So A is 89.99988 degrees. Now, that's definitely not sig figs, but I'm carrying all those decimals along because they're going to be important in our calculation. And then I'll round at the end. But I'm going to need this detail out there to kind of get an accurate calculation. So if you're doing something like this, don't round too early because our angles are like, this is almost 90. So it matters out here in the places where it's not quite 90. Okay? All right. So now what I want you to do, now that you have like angle A, which is also angle B, you know that this is 2AU right here, and then you know what the whole angle at the top is going to be twice P. You could write a sine rule equation that will help you solve for X. So go ahead and pause the video and do that. All right, let's see how you did there. Okay, so I've just got the distance over the sine of the opposite angle. So that's this 2AU distance, which we know from here is 3.0 times 10 to the 8th kilometers. So there's my distance over the sine of the opposite angle. Distance over sine of the opposite angle is going to equal a distance, and I'm picking this one. They're both the same, doesn't matter. I picked this distance, that's my X, over sine of this angle, which is 89.99988 degrees. Rearrange that equation so that X is alone on one side. And now, for the crowning moment, get out your calculator and do that math and tell us how far we are from point A to that distant star. All right, here's what I get. I get 7.16 times 10 to the 14 kilometers. That's a long way away. Now, a comment here. I did this calculation on 3 different calculators and I get slightly different results, okay? If you're using a fancy calculator that does some rounding for you, you might run into trouble because some of these numbers are so tiny or so big that it's going to round and it's going to change your calculation. For example, when I did this calculation on the fancy calculator, it showed me 0.4 or 0.00004. But when I do it on my standard scientific calculator, it gives me a few more numbers after that last 4, which of course is going to affect our calculation. So if you followed along and you got a slightly different answer, that's most likely why. The interesting thing was that it was my more simple calculator that gave me what I felt like was the better result. Now that you've watched the video, take a minute to jot down some notes, some questions, or a quick summary of the lesson. You can also re-watch portions of the video that were a little bit challenging the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.